So if you'd like, you could just write that as 5. That would be okay. But it's good to keep the 0 around, because that way, well, you'll see. Okay, so let's say, okay, I'll back up for a second. So suppose our goal, right, in this case is to find the current through this capacitor, or just the total current equivalently, right, because it's all in series. What's one way we could do that? Yeah, so we could find the equivalent impedance, and then you could just divide the V phasor by the equivalent impedance and get I. So it's again, that'd be the fast way. If you wanted, you could do node voltage, but that'd be silly. This is better. So we know the equivalent is just going to be the sum because they're in series. So now we take a real and an imaginary impedance, add them together, and we get a complex one. And so our I phasor, this is Ohm's law of impedances, is the bookkeeping number for our for V divided by this impedance, right? Okay, so suppose you want to divide that out. What do you do now? You could do the complex conjugate. Yeah, so I would think of it as they end up being algebraically identical if you think about it. But the denominator, I think the best thing to do is, because you may have more complex expressions, and then trying to kind of bounce around all these complex conjugates and stuff could be annoying. So I like to think of it as going to polar form. So what you end up doing is, if you want to get the magnitude, right, what's it going to, what will the magnitude of this whole thing be? How do you get it? Yeah, so the square root of the sum of the squares. So the square root of the sum of the square of two things which are the same is just going to be root 2 times the original thing, right? And what will the angle be? It will be the inverse tangent of -1 over 1. Yeah. So what I would do to make sure, right, if you want to think about it, let's see. So what you want is this angle, right? So if you want, you can think about it like it is just a formula. It's just the arctan of B over A. But yeah, basically what you'll get here is it should be that line, so it's just going to be -45 degrees or -pi over 4. So if you don't want to think about it as arctan or put it in computer or whatever, right? You know that it's two lines of the same length, so it's just going to be -pi over 4. All right. So that's going to be our, so what is this number again right here? What's that? The I, V, Z? Yeah, that's the equivalent impedance, right? So once we have that equivalent impedance, what we know is that the phasors are related by the Ohm's law of impedances, so it's just this guy divided by this guy. This form is better, why, than the form we had before? So why is this better than this one? Yep. Yeah, so they're both polar. So all you can do, at this point, if you think about what polar means, you can basically just divide out the magnitudes. So you end up with a total magnitude. And if you do 0, so basically it's just one of the complex number exercises on homework 5. When you do these, it will remind you of the fact that the magnitudes is going to be the ratio of the magnitudes and the difference of the angles. So you end up with this final current. Okay. So we have a Yep, okay. And what will omega be when we convert back? Someone over there. 100. Okay. So it's just a bookkeeping number. If you want to go back to the real world, it's just going to be that number right there. So what we've done now is we've turned what would have been a really annoying trigonometry problem into a really easy algebra problem by doing this trick, right? And we haven't derived every little step in between, but I hope that you get the flavor of why it works. And so then at that point, we have this answer. So this is a really, really powerful technique because it can be generalized to even pretty big circuits. OK, so it's 1:12, so I will call it a 5-minute break. But yeah, OK, cool. OK, so let's do one more thing on this example here. So what we were just saying before is we did this calculation and we found that I of t is equal to this function, right? So let's look at its various properties because we went through and did all this work to find it. So what do we get? So what you find is that the current has the same basic shape as the voltage. It is a cosine. That is good. If you go through and do it a long way, and do the proofs, that's the case. But yeah, you should always get a cosine like that, or a cosine with some offset. What we find is that the current is a lot smaller though than the voltage. So this is not to scale, of course, otherwise you wouldn't be able to see this. But you get a much smaller current. And we also see that the current leads the voltage. So in other words, he hits his bottom of his period, and then this guy hits next. And the time between those two is just given by pi over 4 radians. Since it's pi over 4 radians and omega is 100, right? The time it takes to actually move through that much, to move pi over 4 radians is pi over 400 seconds, right? So that's what our voltage and current relationship looks like. So in that sense, whenever you put a pure cosine in, the answer isn't all that exciting, right? You end up just getting a pure-ish cosine out. So also, Luke brought up a good point, which is that here this is in steady state, right? So if you have, so that's sort of like once you activate this cosine, there's going to be a slight delay where there's going to be some distortion as the circuit kind of ramps up to being this shape, right? So typically what you'll get in this case is you would have kind of maybe the first half period or 2 periods or whatever will be a little smaller than they should be. And it's an issue, but hopefully you've designed your circuit so the homogeneous response doesn't last very long. OK. So what else? Let's see. All right, yeah. Well, I guess I'll do a harder one. I'll at least set it up, but you guys can tell me if it's worth actually going through and finishing. OK. I'll also mention, so as you guys saw in homework 5, it was non-debugged at first, but I went through and did the solutions, and nothing was broken except for the fact that one of the answers in the back of the book had an error. So, but everything else should work fine, and I gave you the rough approximate answer. Because one of the phasor, or one of the complex number exercises, the number in the back of the book is wrong, and I tried figuring out what was up, but yeah, it's 4D. You'll see what I mean. Okay. So let's say we had a bigger circuit. Okay, suppose we wanted to go through and solve this thing. And what are we trying to find? Let's say we're trying to find VL of t. Okay? So if we wanted to find VL of t, what would we do?